So let's go ahead. So introducing me, I am Harsha Theruvati, Geotechnical Team Leader at MIDAS IT. So today we will be going into an brief idea about the ground structure interaction. So before that, we are presenting you with the MIDAS Geotech webinar series. So it's a monthly webinar series wherein we will be discussing about advanced modeling techniques as well as some case studies. So these are the entire topics, list of the topics. So in today, which is 27th of September, we will be talking about getting started with GTS NX and ground structure interaction. So on 8th of October, we have a training webinar series on excavation modeling. On 25th of October, we have a case study from one of our pro user, WIT Consulting, wherein we will be talking about from high rise to low rise to high rise, the finite element analysis of the heritage sewer impact using GTS NX. On 12th November, we are having a training webinar series on tunnel modeling. And 25th of November, we have a case study, which is on a seismic analysis of a dam abutment. And on 10th of December, we have a training webinar series on ground structure interaction again. So that's the idea. So let's move ahead. Today's topic, which is getting started with GTS NX, ground structure interaction. So we'll talk about ground structure interaction, followed by what are the features that are present in GTS NX, helpful for the ground structure interaction studies. And we move on to the demonstration and then Q&A. So when we talk about ground structure interaction, overall, it is an interaction between the ground and the structure, as simple as that. And that can be useful in high-rise building projects, in deep excavation projects, in tunneling projects, in all the projects wherein the structure is interacting with the soil. So in this session, we will be discussing about the ground structure interaction, so what it is and why it is needed. And later on, what are the various methods present in the industry, used by the industry, and the limitations accordingly. And then we will talk about the detailed analysis using soil continuum method, which is the recommended procedure. So on the fun part, this is how the interaction between the ground and geotech and structural engineers can happen. So structural engineers ask for the stiffness, and geotech engineers ask for the load. So geotech engineers can only provide the load, can only provide the stiffness when the load is known, and structural engineers can provide the load when the stiffness is known. So this cycle always goes on, and anyone between these two has to make a prior assumption and provide with the loads, and then later on the stiffness will be provided, and that's how the cycle will continue. So the first part, what is ground structure interaction? So it's an interaction of stiffness and deformation between the structure and the soil or ground, or soil or rock, basically the ground. And it is necessary for adequate assessment of stresses and forces in the supporting structure. So that is the necessity. And why is it needed? So whatever the changes in the stiffness that is happening in the soil or rock, that will affect the forces in the superstructure, or that it will be affecting the forces in the entire foundation, that will be affecting the forces in the deck. So overall, the entire structure behavior will change if the stiffness of the soil is changing. So that's why it is very much needed. And in an overview of various methods that we have for ground structure interaction studies, we have two methods. The first method is substructure method, and the second one is a direct method. So in the substructure method, what we do is we just create the superstructure, and at times we create the substructure along with it. But we won't be modeling the soil as a continuum. What we do is we model the soil as in springs here. So we just provide soil springs, and that soil springs is acting like a boundary condition, and that will support the superstructure. So the forces are dependent on the stiffness that we provide here, the forces in the superstructure. So that's the substructure method, and we have various methods for it. We have a Winkler springs, Bowles method, and many empirical equations depending on the requirement and importance of the project. One can go further. So that's the substructure method, wherein we will assess the stability of the superstructure separately and assess the stability of the substructure separately. That's how the substructure method works. And in the case of direct method, we will be modeling the soil as a continuum directly. And then along with the superstructure and substructure can also be modeled. Otherwise, only substructure and the soil can be modeled. So here, the soil is actually modeled as a continuum. This is where we have a lot of benefits, wherein the variation in the geology, the variation in the the nature, material nonlinearity of the soil, basically the plastic nature of the soil, can also be considered. So that's how the direct method is the one of the best method that can help you out with the like a proper assessment of a proper detailed assessment of the entire superstructure, structure, any kind of structure. So this is only possible via numerical methods. Any continuum methods like finite element method or finite difference method or boundary element method, any kind of method that will that are present. There are many methods present, so those will be very much helpful to determine the direct method for any structure, any project. So now we'll see what are the various GSI methods. So first thing is the very preliminary method, wherein the method like Ball's method is coming under this particular category. First thing is linear springs. We get either the compression only or tension only, depends on the project, but it's linear in nature. So whatever the load is coming out, that will be like in a linear proportionality with the displacement. So it's a linear spring. So it's basically the soil is considered as elastic medium here. And the next one is multilinear springs. So here, like there are many methods again. So those methods will be very much helpful in considering the plastic nature of the soil and at times the non-linearity nature of the soil. Suppose, let's say, from origin onto the positive side or first quadrant of this graph, this is like a tension part, and the third quadrant is like compression part. So here, until the yielding point, it's a kind of multilinear, or we can consider nonlinear. So it's not perfectly linear. So hence, it's a nonlinear in the elastic part. And later on, after the yielding points, it's perfectly plastic, a kind of pure plastic material, like a more Coulomb material kind of thing. So here, this kind of stiffness is provided to the soil spring. So this is the multilinear springs procedure. So there are many methods that will help you out in determining the multilinear springs. So there are many methods like BM, Lehane theory, or basics theory, and so on, will provide you with this multilinear springs. And these methods are again classified for different methods for soil and different methods for rocks as well. And there are another methods which are basically from empirical relations, which is PY curves. So these are very common method for more detailed analysis that are determined according to Rees et al. Theory, Matlock theory, and then and there are many equations provided by American Petroleum Institute as well. So what happens here is, like as you know, the normal like stiffness of the soil actually varies along the depth. So when the load is applying onto a pile, let's say, the top part may be reflecting very more because the stiffness is very less. As you go down, the confining pressure increases, the confining stress increases, and the behavior of the soil changes as you go down. So this kind of behavior can be considered using PY curves. So this is one of the better method in terms of considering the soil structure interaction. And the next method is soil continuum method, wherein like this is the method for direct method. So this is the method that can come under the direct method of the interaction studies. So wherein let's say for a pile raft foundation, we have different kinds of interactions. So we have interaction with the raft and the pile and the soil, pile and pile, and raft and soil as well. So there are many kinds of interactions. So let's say if we consider this system in the substructure method, wherein the soil is modeled as springs, we are not considering the pile and pile effect. That means pile group effect is neglecting. So this method is this method is able to consider the pile group effect as well, the soil continuum method. So hence this method is very much helpful in terms of detailed analysis. So we'll see what are the procedures that we have in soil continuum method. Okay. So firstly, in terms of soil continuum method, we have one method for manual application. So wherein the structural team will provide you with the load combination. So we get the loads from the superstructure. So in terms of high-rise buildings, let's say, so we have loads from the superstructure. And as a geotech engineer, we provide we model the foundation, and we model the soil as a continuum. So that's the idea. We model the foundation. Maybe it's a simple raft foundation or raft with the piles. So we have the foundation model, and we have the soil layers model. All we do is we apply the load. So to get the loads, we have various options. You can manually apply loads at each and every point, or else you can import it via tables in this software GTS NX. That will be easy when you're dealing with hundreds of loads and hundreds of load cases. So it is easy to import the loads via tables. So this is the second step. The first step is modeling of the foundation and modeling of the soil. And the second step is importing the loads. So here we are not actually modeling the superstructure, but we are just modeling the substructure and the soil layers. And the load coming up from the superstructure is just applied on the foundation. So what we get out of this is we can do the stability assessment of the entire foundation. So we can get the displacement, we can see the soil bearing checks, and we can see the lateral deformations and so on. So based on this study until now, we can get the stability assessment of your substructure. But let's say you want to, like as a geotech engineer from this study, we want to provide some soil spring stiffness to the superstructure team. In that case, what we do is we will extract the results from this particular model. So at each and every point in the model, the displacement may be different, and the soil pressure may be different. So the pressure versus displacement. So we may get the separate reaction modulus, or you can simply calculate the force deformation curves at different locations of the foundation. And this force deformation curves can now be exported to the structural team, wherein they will use it as an soil support, maybe as a multilinear spring, and proceed on with the analysis for design as well. So this studies is called design optimization studies. Initially, the structural team uses some preliminary soil soil stiffnesses, and then they run the analysis. They give us the loads, and we use that loads for the stability assessments. And later on, we provide a new stiffnesses, and then that stiffnesses will be taken back to the structural team. This will be very much helpful for design optimization. So that's the manual method. But this entire method, we will be dealing with a lot of Excel sheets, and then the graphs, and then there might be it might be a tedious job for both structural and geotechnical teams to deal with the Excel sheets. So now we have some recommended procedure using the MIDAS GTS NX family program. So suppose, let's say we have an high-rise building model, wherein we model the superstructure along with the substructure in a software called MIDAS. It's like the building analysis and design tool from MIDAS. So this entire superstructure along with the substructure will be transferred to GTS NX, and we will model the soil as a continuum here. Okay, so the soil is modeled as a continuum, and then the reaction from the MIDAS gen, the reactions for various load combinations, will now be taken back to GTS NX and applied like a loads. Okay, so now the loads are applied here. So in the previous method, we are applying loads via Excel sheet, but now in this method, we are applying it via the direct transfer between MIDAS gen and GTS NX program, so which is an automated procedure. So because of this, we will be now able to understand the stability of the substructure. So you will be able to check the lateral deformation, settlements, and the bearing pressure checks, and so on. Then that's the first step, stability assessment. But let's say you want to proceed with the optimization, design optimization studies. In that case, whatever the first deformation curves at different points in the let's say the substructure, like every depth of the pile. So we can take that pile, that first deformation curves, and those first deformation curves will be exported to the structural team. and now the structural team can able to use it as a new springs for the substructure. And because of that new springs, the force in the like superstructure will now change. So now the design optimization can be done using the force deformation curves. So this force deformation curves can be of various nature. It can be simple linear, it can be like a non-linear, and hardening behavior can also be considered. And even of course the plastic nature will definitely be considered, because we are going to use some plastic soil materials, like maybe hardening soil or morculum or modified morculum and so on, depends on the geotechnical report. So this is responsible for the design optimization studies. Then, so what are the advantages from this soil continuum studies? So we have advantages in terms of plasticity. So we can consider the plastic nature of the soil. Then we can consider the pile group effect, and we can consider all the geotechnical and geological features, such as the topography, as the terrain changes, the confining pressure changes, and because of that, the stiffness of the soil may change. So all the geotechnical and geological features like topography, straight faults, etc., can be considered. Then the time dependent of properties of the soil and concrete can also be considered. Let's say you're dealing with clayey soils and soft soils, and you want to consider the consolidation effect as well. So you can run the consolidation analysis in the GTS NX software along with the loads that are coming from the structural team. And then you can able to understand with respect to time how the stiffness is changing as well. So this kind of time dependent calculation can also be done. So this is one more advantage. And then this method at first can be used as a check. That means just to run the stability assessment of the substructure to understand the deformations, bearing pressure checks, as well as the lateral deformations and the settlements. And for design optimization, we can take back the springs, and then that will be a new springs to the structural team, which will be used for the analysis and design of the superstructure. So that's the idea. So these are various advantages that we can get when you are dealing with the soil continuum method. So this is the recommended procedure, wherein instead of manually applying the loads, you can use the MIDAS structural programs to be able to automate the procedure. So that's the idea about the soil continuum method, and the overall idea about the ground structure interaction studies. Then if we move to the GTS NX, so there are many features in the software that will help you out in like modeling the substructure along with the soil as a continuum. So we will see how that will help you out in your projects. So firstly, so we'll talk about the workflow in GTS NX, and what features of this software will be helpful for ground structure interaction studies. So at first, this software has three classifications in terms of geotechnical modeling. So we have axisymmetric modeling, 2D and 3D modeling. So all these three modelings can be done under one roof, which is GTS NX. So this will be helpful if you are dealing with 2D projects or 3D projects, even axisymmetric. So with one license, you will be able to access all the three platforms under one roof. So this is the general workflow in any FEM theory, FEM softwares, and even GTS NX is no exclusion from it. You can, first thing is we create the geometry. We either import it or we create it directly in the software. And then we assign some material properties. So in terms of this GSI analysis or ground structure interaction studies, we can assign the material parameters like plastic parameters, maybe the hardening soil or modified morculum and so on. So basically considering the entire non-linearity and plasticity in the model. And then we assign some properties wherein the 1D properties, 2D or 3D properties. So since we are modeling soil as a continuum, we'll be dealing with 3D elements. And for the superstructure modeling, we will be considering the 1D elements or 2D elements, depending on the modeling requirements from the structural team. Then we move on to the meshing. So we disgrace entire geometry into a mesh, and we apply loads and boundary conditions. We run the analysis and get the results. So this is the basic workflow. So from now onwards, I'll be giving you an idea about the features that are very much helpful for GSI analysis in each and every aspect. So let's start with the geometry. So firstly, whenever you're dealing with GSA analysis, we are dealing with, in the case of high-rise buildings, we are dealing with various raft modeling, various excavation-related works, and various pile foundations. So modeling of line or curve or and polyline is very much easy in this software. So you can utilize the features that are very similar to regular CAD softwares. So if you're acquainted with any CAD tool, it is easy for you to jump into GTS NX and straight away start modeling. And apart from modeling, you can also import various AutoCAD files. Maybe you can import the DXF files or DWG files or many other CAD files like like IGS format, ACIS format, and Parasolids format, and so on. So this is how it works. Suppose you have a CAD drawing, you can simply export this as a DXF or DWG file, and then you can then import it back to GTS NX. So the importing of any raft related modeling or any excavation related modeling is, or any kinds of CAD tools, is very much easy in this software. Then, now we are talking about a high-rise building and the ground structure interaction for the high-rise building here, because I'm going to demonstrate the same in the upcoming demonstration part. So in that part, let's say you are dealing with lots of terrain, and as well as, I mean, the terrain is not smooth, but the terrain is actually undulating along the length and breadth, and you have a lot of soil layers. So there are many features in this software that can help you out in creating this kind of model in very less time. So if you may create any kind of solids that are changing its length, it's changing its direction along the length, or you can create the terrain and soil layers easily using the features present in the software. So we have one such feature called Terrain Geometry Maker. Suppose, let's say you're dealing with a hilly terrain, you can simply take the contour data of that particular terrain, and that data can now be converted to a surface. So now the surface has been created. With respect to the soil layers, you can simply use the bedding plane wizard, wherein you can import the entire borehole data, and using that borehole data, we can use we can create the soil layers. So using soil layers as well as terrain, the entire continuum modeling of the soil has been done. Then the substructure and the superstructure modeling can be either be imported or be modeled directly in the software as well. Then now we will talk about each aspect of the workflow and the features that are helpful for you. So firstly, the auto connect feature. In the case of high-rise buildings where you have hundreds of like pile caps and raft bodies with you, so you might be dealing with hundreds of solids in the model. So we need to make sure that each solid is connected to the surrounding solid, so that only then you will be able to have the proper stress transfer. So here in this software, you will be having a feature called Auto Connect, wherein that will be helpful for you to connect each and every solid with the adjacent one. So thereby no meshing issues, and thereby very less or no divergence issues in the software. So it will be helpful for you when you're dealing with this kind of structures. So let's say we have a very huge raft, like maybe 2 or 3 or 4 meter thickness, and there are many pile caps next to it. So you have like hundreds of solids here, and these solids should be in connected with your soil layers. So when you're dealing with this kind of modeling, so we need to make sure that these solids are connected with the surrounding soil layers as well as raft, and this can be like completely achieved using this auto connect option. And we also have one more feature, which is imprint. Suppose you have like hundreds of piles in the model, and these piles should be in contact with each soil layers. So we can simply use imprint option, wherein we will select all the piles, and then we select the soil layers and use the auto imprint. The software will make sure that pile is connected to each soil layer. So it's like imprinting a 1D element, which is the curve, onto a 3D solid geometry. So this kind of feature will be very much helpful when you are dealing with the piles. Then, in terms of pile simulations we have various methods, right? So many people prefer piles to be modeling as a beam element, and some people prefer to model it as a solid element. So this is one more advantage in this software, wherein you can model entire the foundation based on the kind of modeling you wanted, such as pile can be modeled as a beam element. So that's one way, wherein you will be able to see the bending moment, shear forces, and so on. But let's say if the diameter of the pile is very high, maybe let's say 1.5 or 2 meters, and the length is pretty big, in that case, maybe the beam element may not be helpful because of the depth and the width ratios is very high in that case. And in that case, you can go ahead with the volumetric piles. So we will be modeling the pile as it is, like we will model entire pile as a solid model, and then you can assign a concrete property to that particular solid. But let's say you're dealing with hundreds of piles which are as a beam element, but you're unable to make sure that these piles are in proper contact with the surrounding soil layers. In that case, we can use embedded elements, which is embedded beam element. There is no need to make sure that piles is in node-to-node contact with the soil layers. We can simply make sure we can simply provide embedded beam element, and software will automatically assign and interpolation elements between piles and the soil layers automatically. No need to worry about the connection here. And let's say you want to control the behavior of the pile by providing the like a skin friction and the end bearing. In that case, you can use the pile interface in the software, wherein you can provide the skin friction resistance based on your pile load test, or else based on any empirical equations. And similarly, we can provide the end bearing resistance based on analytical or empirical or pile load tests. And when you are using volumetric piles, but still we want to control the behavior of the pile by providing some skin friction and end bearing resistance. In that case, we need to use interface element, which is plane interface now. So this is these are the various ways to model the piles in this software, and it can be helpful to create any kind of foundations, and that will be very much helpful for soil structure or ground structure interaction studies. Then let's say we are dealing with solid elements now, but solid elements has only 3 degrees of freedom, which are translations in X, Y, and Z directions. It can simply deform, but there is no rotation, so hence you won't be finding any bending moment or shear forces over there. So to overcome that, we have 2 methods, which is gauging shell method and the virtual beam method. Okay, so in the gauging shell method, what we do is whatever the raft that was modeled as a volumetric or solid element will be assigned with an gauging shell, which is a non-structural member and no stiffness member that will be calculating all the forces that will be taking the all the forces in the soil in the solid of raft, and that will be calculating the bending moment, shear forces, and so on. Similarly, we have a virtual beam wherein we can assign a virtual beam to an 2D element or a 3D element, and then that will be calculating the bending moment and shear forces and so on. Similar to gauging shell, it's a non-stiffness member and does not have it's a non-stiffness and non-structural member. It's just calculate the forces in your 2D or 3D elements and provide the values in terms of 1D or beam element. So it will provide you with bending moment, shear forces, and axial forces, and so on. So this will be very much helpful when you're dealing with solid elements, because it is not possible to use beam element at times when you're dealing with low D by B ratios and for 2 meter or 3 meter diameter piles and so on. So and then the meshing feature is also very much helpful. So as I shown you in the previous slides, you are dealing with hundreds of solids, hundreds of wrapped solids, but making sure that these solids are connected to each other via meshing is pretty much needed. So for that, we have 2 different meshings here. So we have a tetrahedral mesh, wherein that can be useful for any kind of complex geometry. But only thing is this will end up having very huge number of elements. So that might be responsible for like a lot of analysis time will be very much increasing. So hence tetrahedral mesh is very much helpful when you're dealing with complex layers, but you will be ending up having a lot of elements. And we have a hexahedral dominant mesh, which we call hybrid mesh, wherein you can simply provide hybrid mesh to the any solids that you are trying to mesh. At any stages of uniform solid, it will provide the hexahedral mesh, and whenever the shape is changing, it provides the tetrahedral mesh. So it's a combination of tetrahedral, hexahedral, and pyramid elements, and so on. So then we have a combination as well. So for inner solid, you can provide the tetrahedral meshes, and for the outer solid, maybe you can provide the hexahedral meshes, but it will be able to join both of them using the hybrid elements that we are using here. So even this kind of mesh is possible. So this will make the life of the numerical modeler very easy, because you might end up having very less node-to-node connectivity issues, which will later on very much helpful for analysis. And in terms of loadings, you can apply the loads either on the geometry or on mesh. That's an important part. And all the different kinds of loads, like a beam load, concentrated loads, concentrated moments, and displacement loads. And even the load combinations can also be provided in this software. So, and in addition, you can provide the dynamic loads as well. But let's say we are considering the very high-rise building, which is having lots of columns, and you're ending up having lots of loads. So we have a feature to import the load as a table as well. So you can simply export your entire loads, and that loads will now be imported into GTS NX, and it will be applied at the points where you have provided the XYZ coordinates. And it will be very much easy when you're dealing with lots of load combinations which have lots of load sets. In terms of boundary conditions, so the next step after providing the like loadings is the boundary conditions. So you can assign the boundary conditions when you're dealing with the substructure method. You can assign it as a point springs. This is one way. But when we are dealing with the soil continuum method, we can model the entire soil as a continuum body, and we can assign some point springs, some fixed supports or normally fixed supports at the boundaries. Depending on the model, we can provide basically normal restraints on the vertical sides is necessary. Normal restraints means it's a roller support, and at the bottom or at the base, we provide fixed supports. But if you are dealing with the seismic analysis, wherein you want to provide the infinite continuum, in that case, we need to provide the free field elements. So we in this software, we have free field elements as well. This will be helpful to provide the entire the infinite body. And at the bottom, we can provide either fixed supports or elastic half space supports, whichever is needed according to the studies. So we can provide all kinds of boundary conditions here as well. Then coming to the analysis, we can run a stress analysis, both linear or non-linear in nature, and then we can run slope stabilities, like the SRM method, basically C5 reduction method, or finite the stress analysis method, or limit equilibrium method. All of them can be done in construction sequences in this software. And you can do all the dynamic analysis ranging from 1D ground response to response spectrum and to a time history. So we can do all kinds of dynamic analysis in this too. We can run a seepage analysis. Suppose if you're dealing with excavation wherein you're dealing with a dewatering, so it might be very much helpful. Both steady state and transient can be run. And this seepage can be coupled with the stress to run a stress seepage coupled analysis. And you can do a consolidation analysis if you're interested in time-dependent variation of the soil deformation when you're dealing with clay soils and so on. So all these analysis can now be done in construction stages as well. So these are all direct analysis. If you want to do it in construction stages, we can do that. And in addition, we can do a thermal stress analysis as well, like heat of hydration or fire in the tunnel kind of situation, or ground freezing technique. So in such a cases, we can do this construction stages for thermal analysis as well. And once the analysis is done, interpretation of the results is very much needed, because the behavior may changes from each step to each step in each construction stages as well. So understanding the model behavior is very much important step in the numerical modeling job. So here we can get the results in terms of contours, graphs, animations, cutting planes, section diagrams, and we can even get the reports, and we can get the graphs directly out in the report as well. So these are some examples. Suppose you're dealing with a very big model and you want to consider the see the bending moment in various files, but maximum and minimum want to be seen at the and the location want to be seen. So this is how you'll be able to see the entire results of the files, and then you can see the max and minimum result. And you can see the animation results along with the cutting plane as well. So we have cut a section here, and then we are able to see an animation of the deformations in different stages. So we can see the graphical output, we can see the tabular output as well. And most important thing is, whenever we are trying to interpret the results, we need to worry about the results at each and every position, not just the contour, but what is exact value at the particular location may also be needed. In such cases, we have an option called result tags, wherein you can simply place the point at various location, and the result will be shown. And you can also place the result at a particular section as well. And you can get the 3D PDF report, so wherein you can simply access the model just like how you access it in the software. So it will be very much helpful for presentation purposes. So all the model related details, the load related details, as well as the results can also be seen in the case of 3D PDF. And we have an option to export the result in an Excel, so wherein we can get the tables, we can get the graphs, and we can get the snapshots as well. So this will be helpful as a small part of your bigger engineering report. So that's the idea in terms of the ground structure interaction and getting started with GTS NX. Now what we will do is I will do a modeling demonstration for a manual method which I've shown earlier, the soil continuum method for manual application of the loads. So which we will be doing it in next 10 minutes. So let me show you the software. Give me a minute. So whenever you're opening the software, it will ask you to go choose between 3D, 2D, or axisymmetric. So let's go ahead with the 3D for this time. And if you remember, the first step in the soil continuum modeling for manual application of the loads is to model the raft and then model the soil layers. So let's model the foundation at first. So we can use various options here for modeling the foundation, or we can simply import it. So let's import the foundation. So this is the software, how it looks like. And right now, the work plane which you're working is a vertical plane. Let me change to XY plane. So we have XY plane, right? This is a top view. Now let's import the file. We are importing the raft. Okay. So this is the raft body, and these locations, the 9 locations which you are seeing, is the location of the columns. So we are dealing with a high-rise building, and we have an sample raft body, and we have 9 column locations. So the load which is coming from the superstructure will be applied at these locations. Okay. So let's press. So let's press OK. Okay, so we need to change the units before importing. So right now, the import option for geometry is in mm. So we will convert this to meter, and let's import the geometry again. Okay, so now the geometry has been imported. The raft is of length of 15 meters, and this is also 15. So now the thickness of the raft in this case is, let's say, 2 meters. Okay. I will just select the edges of the raft, and then we're going to extrude it in the Z direction. So let's go with the -2 as the thickness of the raft. Okay. And now the next step is to model the soil. So the foundation modeling has been done. In this particular scenario which I'm showing, I'm just creating the raft, which is foundation, only foundation that we have, and there are no piles in this scenario. So the next step is to create the soil continuum body. So here we go. So each box is of 20-meter width by default in the software. You can change the grid size at any point of time. Let's assign at least 3 times the width on either sides. So the width is 15 meter of the raft. So here it is 15, 20, 20, and 20. Or we can go with at least 60 meter on either side. So let's provide 4 on either side. Yeah. So this is the boundary of the soil layer. And now we will extrude this soil layer. So there is only one single layer which I'm going to model in this particular demonstration. So let's extrude this soil layer for like around maybe 80 meters. So we are previewing it and then press OK. Okay. And now, if you see, these are the column drawings that we have provided. So these column drawings should also be considered. So what we will do is, we need to assign the loads at the midpoint of these columns. And hence, what I need to do is, I will imprint these lines onto this raft. Before that, the midpoints of the entire, let's say, columns should be known. So we will be getting that from the sheet from the structural team. Suppose, let's say, this is a kind of reactions that we get from the structural team. So we have various locations of columns, and we have various load cases. So let's say we have load case for the dead load, live load, and the earthquake load. And maybe the structural team can also provide you with the what do we say? The load combinations as well. Yeah. So in this particular scenario, let's consider only the earthquake load for now. Okay. So all the EQX, which is the earthquake in X direction, the reactions corresponding to that will be exported. So I've just yeah, this is the locations of each. This is your columns. So we have 9 columns, and the load which we are considering is earthquake, and we have the coordinates of those particular particular columns. So these are the coordinates. So what we will do is, we will simply control these coordinates, Control C, and then let's go to the software. And let's go to the point option here, and then we'll go to the tabular input and press Control V. So we have all the points here. So let's press OK. So we can see all the midpoints of the column locations has now been imported. So what we will do is, we will imprint those points. So let's select all the points that we have. So we have 9 points. Firstly, we go to the point. The target is to imprint on the surface. So all the points are selected. Yeah, target is the surface, and all the tool objects are the points. And then we can use the direction of shortest path line and then press apply. So now the points have been imprinted. The next thing is to imprint the column the column boundaries as well. So let's select the curve, and then select the surface, and the tools as the column boundaries and direction of shortest path line. So now we have imprinted the midpoints of the columns and as well as the column boundaries, right? That's the modeling that we have done. The geometric modeling will now be completed when you go with the auto connect option. So what this auto connect option does is, Right now, we do not have any proper connection between raft and the soil. Those two are hanging in the air. So if you check this duplicate, so check the duplicates, we do not have any common faces between the raft and the soil. So these two are just hanging in the air. So what we do is we select this auto connect option. So this is the auto connect option. Select both the solids, and then with one click, we will be able to see the raft and the soil connected to each other. So if you go to the check duplicate option and click apply, so you can see a common face. So these common faces represents that two solids are connected to each other. That's the idea. Then let's go for the material definitions. So the first thing is we'll go with mole coulomb for soil layers. And elastic modulus is 50,000, unit weight of 20, Poisson's ratio of 0.3, and cohesion of 30 and friction angle of 36. So that's what we are going to define for soil. So click on apply. Then change the material to elastic for concrete definition. The elastic modulus is a 2E7, let's say, and unit weight of 25, Poisson's ratio of 0.2. Apply. Then we need to create a very high rigid body. So what we do is, I will tell you the importance of the rigid body later on in the case of modeling. So I'm going to provide the rigid body with 2E8, and any unit weight should be fine. Press OK. So the high elastic stiffness could represents with the rigid behavior. So now the next thing after the creation of material is to create the properties. So go to this property tab, and here in the create option, we will go with 3D for soil, and then for concrete, which is raft. Click on apply. And we will assign the rigid body as a shell element. I will apply this shell element to a particular location. We will talk about that. Rigid body. Okay, let's perform the meshing now. So go to 3D, select the solid, and here let's provide a mesh size of 0.5 meter. We'll go with the hybrid mesher, raft, give the name raft. So you can see because of the imprint, the software is able to provide a node at this location. So that's the advantage of imprint option at the column midpoint location, because that will later on be helpful for assigning the loads here. Okay. Now select the soil. So we'll go with the 4 meter mesh size and soil. Provide soil and press OK. So now the soil is actually getting created. The mesh of the soil will be done, and already the raft has been created. Then we will be assigning the boundary conditions followed by loads. So that's the idea. So let's assign the boundary conditions once the meshing is done. Yep. Yes, the meshing has been done. So this is the mesh. So we provided 4 meter mesh for the soil and the 0.5 for the raft, so that the software can able to adapt to the inner mesh size. So you can see the meshing gradient from small to big. So 0.5 over here and 4 meters over here. So both are interconnected. So that's the idea. The next step is to assign the boundary condition. So let's go to the constraint. Auto constraint. So we'll provide GS, which is ground support. And the self weight is applied by default in this software. If you want, you can remove it as well. Now, the next thing is to apply the loads. So if you remember the Excel sheet that I had shown you earlier, so we have Fx, Fy, Fz, and Mx, My, Mz at each column location. So this is the column XYZ coordinates for the particular load combination that we have. So now the idea is to import this entire load using the tabular input. This is a very simple model. we can simply go into the software, take the let's say fourth load, and since we know the location of the pile, location of the column, we can simply assign one by one. But if you are dealing with a very big structure, you have hundreds of loads and hundreds of nodal locations. So it would be very much difficult to apply manually. So that the option of load table import will be very much helpful for you. So this load table import option will now be using by me, so that we can apply the loads via load table import. So for that, firstly, we will take the nodal locations of this entire raft. So nodal points of this entire raft. So what we do is we'll go to the mesh, and here in the mesh, we have an option called table. So we'll go with the node table. So click on none and activate only raft. So yeah, this number represents the node numbers, and these are the locations. So just for the raft, we have a huge number of nodes presented. So what we will do is we will just Control C over here, Control C, and go to the Excel sheet, and we will provide here is a Control V. So these are your like XYZ coordinates, and here we have various node numbers. So we have like around, if you see, yeah. So more than around 6,000 nodes are present here just in the raft. But all we need to do is we need to figure out what is the node number corresponding to these XYZ coordinates, right? So that's what we are going to do. So for that, we will use VLOOKUP option in Excel. So let's provide a helper at first. So to consider the VLOOKUP, I'm going to provide an helper option. So firstly, let's give the column name as helper, and equal. Firstly, let's provide X coordinate of the first option, and apostrophe, and vertical slash, and then apostrophe, and the next coordinate, and apostrophe, vertical, and M4, sorry, M3. So we got a helper. So we just combined all these three. So now we will be doing it for all the 9 coordinates. Okay. Then we will do the same for the XYZ coordinates that we have taken out from GTS NX. So these are the nodal locations. So let's do the same. This is the help. So I will do it again, which is Y2 and yep. Now the helper file has been created. So the entire helper sheet has now been updated. Okay. So the next thing is to just assign the node numbers here. So what we do is we will just Control C all the node numbers, and then paste it here. So we have the helper file and the node numbers. Okay. So now let's do the VLOOKUP option. So we are going to, firstly, we are going to look up a value of this in the table array. So let's provide in the table array of these 2 tables. So helper and the node table here. And okay, so then go up, comma. So in this table array, we are going to look for these values, and then we need to get the node numbers So we have second node column which we need to get up and provide 0. Yeah. So now we have all the node numbers. So the node numbers corresponding to 0, 0, 0 coordinates is 2642. So if you go to the 2642 node number, so here we go. So 2642 node number have XYZ coordinates. Okay. So that's how the software is now able to bring the XYZ coordinates and the corresponding node numbers. So now we have the node numbers, we know the XYZ coordinates, and we know the forces Fx, Fy, Fz, and Mx, My, Mz. So what we'll do now is we will open an new Excel file. So GTS NX has an option to import these sample, all the load tables, as I said. So for that, this is how the format should look like. So what we will do is we will import this entire format into the new Excel sheet that I had created. So this is for force. So let's rename as force. And we will go for a new sheet here. We will rename as moment. Then, so even the moment has the same like format. So now we can simply go to the new sheet, provide here. Okay. So in the previous, here we go. So let's copy the entire node numbers, and then so let's duplicate. Let's do this. Yeah. So copy the entire node numbers and provide it here. So we'll just keep the numbers. So load set name as earthquake, let's say EQ. And the name as just provide a force, just that. Or maybe just provide 1 and second and so on. So now here we are actually providing so we are going to have none, which is the function. So there is no function, base function, or any sort of function here. So hence none. So this is for moments, right? So here we have it for moments. So let's copy the moments. Control C and Control V. So just copy the numbers. Similarly, let's copy the same into the force table as well. And this time we will just copy the forces. So we have the forces and we have the moments. So let's import this table. So let's save as somewhere. Okay, so now I've saved it. So let's go to the model. So let's import the loads. So now go to the load table import, and this is the one. Yeah. So here we go. So we have the moments and we have the forces already imported into the software. And for any load combinations, you can use the same Excel sheet, just change the values and you can import it. Now the thing is, we have used the raft as a solid coordinates, solid elements here, right? But the solid elements is only going to take the forces, but it cannot take the moments because it does not have a rotation degrees of freedom. So what we will do is we will provide a rigid body at the location of the columns. So hence I created the rigid body previously. So select all the locations of the raft. I mean, not raft, but the columns. And then provide the rigid body. So this rigid body has now been assigned at the location of the columns, and this rigid body will transfer the forces to your raft, and then raft will transfer to the soil layers. So this is the model, and let's provide some construction sequences. Let's give the name raft analysis. Let's assign soil in the first stage in C2, self-weight and loads. Because of the self-weight, whatever displacement that may occur in the soil, we are just clearing it. New. In the second stage, activate the raft. Save. In the third stage, we will activate the load. Okay. So let's activate the load and raft and the rigid body. Okay. So we'll be running this particular load in 20 increments. So let's create the analysis case, which is the construction stage of raft, and provide the name raft or raft analysis, whatever you think. And the initial stage, we are going to run it for its K0 condition, clear the strain, cut off pressure, and activate initial configuration, estimate initial configuration of activated nodes. So this is then when you run the analysis, you will be able to get the force deformation curves. So let's run the analysis. So I already analyzed the model. So this is the analyzed model for you. So we can see 20 increments and 3 construction stages in situ, raft, and the load. So let's see the displacement. Okay, so this is the displacement which you are seeing it in mm, so which is like around 12 mm. So what we will do is we will see the locations at different points. At each and every point, you can find the result because of the earthquake load that has been applied. Similarly, you can check the cutting plane. So you can see the variation of the load. Since there is moments, you can find not smooth contours because moments are also getting applied. Hence, you can see the variation. So you can even rotate the clipping planes as well. So at any kind of locations you can provide. Now, the idea is to draw the force versus deformation graph, right? So let's hide the raft, and this is the force versus deformation. Like this is the force versus time, the procedure to force versus the load step, sorry. So let's get the displacement. Let's go with the TX translation at first. So at any locations, you can simply select it and then press OK. So for all the locations, you will be able to see the force versus deformation curves. So this is the node numbers and the corresponding force versus deformation curves. So you can see that in the initial stage, the displacement was 0, and later on it reached a high, and later on because of the load increments of moment and forces happening, so there is a little decrease at the location of locations that we had selected. So this is the settlements. Similarly, you can take the result of lateral movements, and then you can also take the total translation if necessary. So let's take the stresses. So because we need stresses as well as displacement, so what we will do is at the same locations, let's go with vertical total stress. Yep. So we have the forces, and we have the stresses, and then we have the displacement. So using these two tables, we will be able to take the force deformation graphs, and that will be exported to the structural engineer, wherein he will be able to use it as a spring. So that's the idea from today's presentation. Sorry that I was hurrying up in the start, and there was an issue in the start.